In this lecture I want to talk about the DC imperfections of op amps. So a quick review to kind of state where we're starting from. We're assuming that we have initially an ideal op amp. And an ideal op amp has a couple characteristics. So first let's go ahead and draw the equivalent electrical model, okay? And it's very simple. All it is a controlled voltage source that's controlled by voltage delta V, and a with controlling voltage terminals V plus. This would be the non-inverting input, and V minus, right? And we would have, I don't know if I'm going to be able to make this look like an op amp, but here we go. And then we state from this that AOL is infinite for an ideal op amp. We also state that the current going into the V plus terminal and the current going into the V minus terminal is 0. And that's equivalent to saying that there's infinite resistance between either one of these terminals and ground, and therefore infinite resistance between those two input terminals. And we would also say that the R out is equal to 0. If I were to put a resistor here, R out would be 0. And we end up with some op amp rules. Ideal op amp rules. Okay, so one, we would say, assuming negative feedback, this is very critical here. Assuming there's negative feedback, V plus is equal to V minus, or otherwise put, delta V is always going to be equal to 0. And that, again, is because just like we can write VO is equal to AOL, the open loop gain, times delta V, we can rewrite this as delta V is equal to VO over AOL, which is equal to something that's finite. Even if it's large, VO, let's say it's really large, it's 100. If we have an infinite gain, something finite over infinite is always 0. So we can, our first op amp rule is that with negative feedback, the two input terminals, the inverting and non-inverting inputs, are going to be driven to be the same voltage. Secondly, we can say that the current going into the plus and minus terminals is equal to 0. Okay, that's an ideal op amp. Now, in this lecture here, we're going to introduce some imperfections that result in our op amp model deviating from this ideal case, and then we'll look at how we can maybe compensate or minimize these effects in some typical op amp circuits. Okay, so the first one we're going to look at is the input offset voltage, VOS. And the way this manifests itself is that VO, it turns out to be equal to the open loop gain times delta V, but plus some small offset voltage. And the way we find this is, let's look in the lab. If we go in the lab and I were to build this circuit. Here's a simple unity gain amplifier, or unity gain, sorry, someone just came in my office and distracted me. Okay, so what I'm going to do is ground this non-inverting input, and then we're going to have unity feedback around from the output back to the inverting input. This is similar to if you had a non-inverting configuration where you might have a resistor RF and then a resistor here R1 to ground. in this case we'd say RF is 0 and R1 is really infinite, and our VI, the voltage that we're applying at the input, is equal to 0. Now for the non-inverting amplifier, the voltage gain, closed-loop voltage gain, is equal to 1 plus RF over R1, but in this case RF is 0 and R1 is infinite, so this goes to 0. So what we have is a unity gain configuration. Okay. Now in an ideal op amp that would have no offset voltage, the expected value, expected VO, would just be equal to 0. But measured value, if we have a good enough meter, will not be 0. It might be slightly positive or negative. VO would be equal to a small negative or positive voltage. And when I say small, it varies on the op amp, but it could be on the order of a couple milliamps, couple millivolts, to perhaps as low as tens of microvolts. Your common low-cost popcorn op amps, like an LM358 or 741, those are going to have you'll measure voltage that could range, could be as large as a couple millivolts. Okay, so what's going on? If we actually have a model, if our op amp really follows this, V out is equal to AOL times delta V. Well, delta V here, delta V is going to be equal to 0, or so it should be. Why? Because of our ideal op amp rules. We have negative feedback. The output is connected back to the inverting input. So we have negative feedback. Therefore, the inverting input, V minus, should be equal to the non-inverting input, V plus. And to boot, V plus is grounded, so therefore not only should delta V be equal to 0, but V plus and V minus should be equal to 0 as well. But we find that VO is actually not equal to 0. It's equal to something, let's say 1 millivolt. And now we find that delta V is actually equal to minus 1 millivolt. That's weird. So if VO is equal to 1 millivolt, then this would mean that delta V is equal to minus 1 millivolt. Okay, so how do we actually modify our model to capture the fact that we don't actually have a delta V of 0? Well, first, maybe let me clarify that if we were now to set or use this op amp in a different circuit, let's say that R1 and RF were not open and 0, but they were like both 10K. Right? So what I would expect there, or what I would find, is that if I measure the difference between V plus and V minus, I still measure minus 1 millivolt. In fact, I measure minus 1 millivolt all the time. So it's kind of like the voltage is the delta V follows this ideal rule that the differential voltage between V plus and V minus is 0, except it's not 0. It's something fixed, but it's something small and non-zero. It's minus 1 millivolt. And so this is not due to the possibility that my open loop gain is not ideally infinite or really, really big. It's because there's actually another voltage source inside my op amp. I mean, not really a voltage source, but we can model what we're seeing as by adding in a voltage source. And that's what we add here. So consider the case where and maybe I should write this as yeah, I'll leave it like that. What I'll do is I'll call this here delta V prime. Okay, consider the case where delta V is equal to 0, then actually VO would be equal to AOL times VOS. So it's not equal to 0 as I would expect. Now let's actually analyze. That probably didn't help at all. So let's go and analyze the unity feedback. Unity feedback amp. Okay, let's analyze it using this model. Analyze. Okay, so what I have is I would say V out is equal to AOL times delta V. We'll start with that. And what is delta V? Delta V is equal to V plus minus V minus, and V plus is equal to 0, and V minus is equal to V out. So let's plug that in. We'll have VO is equal to AOL times 0 minus VO plus VOS. Then we'll collect our VOs, so we'll have VO times the quantity 1 plus AOL is equal to AOL times VOS. And finally, we can write VO as AOL over 1 plus AOL times VOS. If AOL goes to infinity, right, ideal op-amp, that's what we're still assuming, even if it's not ideal, if it's large, realistic op-amp, real op-amps have large open-loop gains, could be on the order of tens to hundreds of thousands. Then we would have that VO is equal to VOS. So, therefore, if I measure VO to be equal to 1 millivolt in lab, given the unity gain op-amp circuit, then I know that VOS is equal to 1 millivolt. Okay, so by adding this offset here, we have found that we can explain, using this adjusted model, what we actually see in the lab. So let's think about how we might modify our circuit, our op-amp circuit schematic, so that we can include this effect. Okay, because this expression here, although correct, is not the most efficient or concise way to state this, or to use it, I should say, when you're doing op-amp analysis. So what we're going to do is I'm going to draw the op-amp. I will put in my controlled voltage source here, V out. I'm going to say this is AOL times, I'll call it delta V prime. Okay. Then I'm going to add in, to make sure I do this right, if we say this is plus and minus, so this is V plus, V minus, I'm going to add in a voltage source here, plus, minus, I'm going to call it VOS. And now this voltage internal here is actually delta V prime. Okay, so that's my model. Another way we can do this is we can model we can model using an ideal op-amp. Okay, let me show you how you do this. And this is the way I like to do it. I like to keep using an ideal op-amp, plus and minus here. And then what I do is external to the ideal op-amp, I have to add in my VOS. And the thing that's always tricky, I have to think about this too, I'll get the sign wrong, is that I need to actually, let me think about it even now. Oh dear, let me pause because I'm confusing myself for a second. Let me pause and then I'll make sure I put this in right. Actually, that wasn't hard. Just couldn't think on the fly. Okay, so you add in your VOS externally. Okay, so let's apply this. Let's apply this to an inverting op-amp circuit. So our inverting op-amp circuit is going to be R1 going into the inverting node. We'll have RF or R2. RF connects to V out. R1 gets grounded because it's inverting. No, it doesn't. R1 actually goes to our VI, right? That's our input. And then V plus is what goes to ground. Okay. Now this is an ideal op-amp with VOS. So if you're given a problem and you said and you're asked to solve for VO, and it's the op-amp is ideal in every way except that it hasn't VOS, how do you solve it? So the way that I'm suggesting to solve it is redraw the circuit and add VOS externally. Okay, don't try to add it internally to the op-amp, just add it externally. And so I put it in series with whatever's connecting to the non-inverting input. And the non-inverting input connection is just a grounded connection. So here I just ground my VOS. Okay, so by inspection, I can write VO is equal to the superposition of two inputs. I have VI and I have VOS. And I'm going to treat VOS as if it's another external voltage source, even though physically there is no voltage source VOS in the lab. Right? The VOS is somehow buried inside the op-amp, and we don't even know what it's due to. We just know that we can describe what we observe by including this offset voltage in our definition up here, our expression for VO as a function of the open loop voltage gain and our delta V. So I have two sources. If I turn on just VI and turn off VOS, I have an inverting op-amp, right? And that's going to give me the minus RF over R1 VI. Okay, this is due to VI alone. Okay, and now I turn off VI and I look at just VOS, and when I turn off VI, R1 gets grounded, and we now have a non-inverting configuration. Right? So the gain for a non-inverting configuration is 1 plus RF over R1, and that's going to be times VOS. Okay. Now, let's think if this is, let's check if agreeable or agreement with the unity gain example, lab example. Okay, so for that lab example, or for the unity gain, we have RF is equal to 0 and R1 is equal to infinity, and VI is equal to 0. So when you plug these in, we get VO is equal to 0 plus 1 times VOS. Okay, and is that what we found up above? We found this right here, right? So this checks with that. Okay, so to recap, to include the offset voltage in an op-amp circuit analysis, you can simply proceed. Oh, I forgot to write this is an ideal. I'll put an I inside my op-amp. So this is ideal op-amp. You take your circuit that you're given and you replace the op-amp with just, or you put an I in it to say this is an ideal op-amp, and then you physically, on your schematic, add the offset voltage, and the polarity of the offset voltage, VOS, is that it's positive goes into the positive or non-inverting input. And then when you solve it, it's just a matter of adding this second component by doing superposition. So it's very simple to include in your analysis. Okay, now let's move on to our second imperfection, DC imperfection, and this is the bias current, IB. Bias current IB. And what we're going to do is we're going to assume, for the presentation here, we're going to assume op-amp is ideal in every way except for IB. In the end, the problems we typically solve or we encounter is that we're going to have a combination of VOS, IB, and IOS. But as I talk through each type of imperfection, we will consider just one at a time. So, in other words, what this means is we're going to set VOS to 0 for this portion of our lecture. Okay, so what this affects, okay, this requires modification to our ideal op-amp rule 2, to ideal op-amp rule number 2, which is that I plus is equal to I minus is equal to 0. Because in fact, in the lab, although sometimes it's difficult to measure this because it's such a small current, you will find that actually there are currents flowing in or out of the positive and negative, or the inverting and non-inverting inputs of the op-amp. So how do we model this? I'm going to go straight up with modeling this, or giving you a model in this case. So here's an ideal op-amp, and what we're going to do is we're going to add 2 independent current sources to our op-amp, and these will be IB. I'll call it IB. What should I call it? IB plus, and IB minus, just corresponding to the inverting and non-inverting inputs. And then we can, if we want to wrap this inside our our non-ideal op-amp, right? We would then have, this as a whole is an ideal op-amp having non-zero bias current. Okay, so we're going to use the same method as with the offset voltage. When you analyze a circuit that whose op-amp you're told has some bias current, you replace the circuit or the op-amp with an ideal op-amp. You write I in there, and then you're going to, on your schematic, add in these 2 bias currents. So what do these come from? Well, inside the op-amp, typically what you're going to have, let's say it's a bipolar op-amp stage. It's a bipolar based amplifier, op-amp, sorry, my brain and my mouth are not in sync today. So example would be the LM358, which is it's a bipolar process. That means it's fabricated with bipolar junction transistors. There are also FET or MOSFET based op-amps. So the 2 inputs on the op-amp ultimately are going to be connected to some base of a transistor. Okay, this is part of what's called a differential pair. Differential pair or a long tail pair. It's not something I would expect that you would have seen if you've just had a first circuits and electronics course, but all we need to know here is that if you know anything about bipolar junction transistors, they're current controlled devices. So there is current that flows into the collector, in this case IC, and that current is equal to some current gain called beta times the base current, and here's the base current, IB. In other words, for a finite beta, which of course the beta, the current gain is not going to be infinite. Let's say it's 200. Okay, say. Well, if you're trying to control through your collector, say 100 microamps, then it's going to take a half a microamp coming into your base. And what this means is that although the current going into the inverting and non-inverting inputs of your op-amp are very small, I mean they're not zero. They're going to be small, but they're not going to be zero, as our ideal op-amp rule says. In this case, the differential pair that I drew, the current is clearly entering into the base. But there are other configurations, and this all depends on the construction of the op-amp. You could have one, a front-end differential pair, where the transistors are arranged in this fashion. So you have current coming out rather than going in. So when we talk about bias current on an op-amp, the direction, polarity of the bias current is never specified. If you look up the data sheet for a particular op-amp and it says typical bias current or maybe maximum bias current over the full temperature range, or maximum bias current at room temperature is 40 nanoamps. Okay, say 40 nanoamps. They're not going to say it's plus 40 nanoamps or minus 40 nanoamps. It could be either. And you are to design your circuit so as to, if you're going to try to deal with this, your circuit modifications will have to accommodate whether it's a positive or negative bias current. The nice thing is that if there's a bias current that's coming out on the non-inverting input, say out here, then the bias, sorry, that would be wrong, let's say it's going in, as would be the case here, then it also is going to go in on the inverting input. All right, so that is going to be consistent because ultimately the polarity of those bias currents are going to be a function of the actual circuit topology inside the op-amp, the implementation. So fortunately, also because because of the ability to just represent the internals again by some simple element, in this case 2 independent current sources, we don't really have to worry about what's going on inside the op-amp and the transistor differential pair or anything like that. I'm just giving you that as a little bit of a background or under the hood so you know what the nature of the underlying nature or mechanism is for why we have some currents, some bias currents in our op-amp inputs. And these currents again are very small. So I think for the LM358, which is an op-amp that we use a lot in basic instructional labs, I think it's on the order of 40 nanoamps. I could be wrong, but 1,000 nanoamps is a microamp, 1,000 microamps is a milliamp. All right, so it's a small current, but yet it's something that sometimes can be important, and I'll show you where it might be important. So let's do an example analysis. So again, let's consider our inverting amplifier. Inverting amplifier configuration. So here's my circuit, RF, R1, and I ground my non-inverting input. I have some voltage source VI over here and VO. Okay, and the op-amp is ideal, but with a bias current. Okay, so we're going to redraw this. In fact, I'm not going to redraw it. I'm going to just add in my current sources to expedite this. Okay. I'm going to hang 2 current sources to ground. And at this point, we're going to say that IB plus is equal to IB minus is equal to IB. And actually, the last imperfection we're going to look at is IOS, which is input offset current. And that one is simply to capture the cases or the fact that the bias currents between the at the non-inverting input and at the inverting input are not precisely the same. There's a slight difference between them. Okay, but we'll deal with that as our last imperfection. So for right now, we're going to assume that there is no offset between these two bias currents. So I'm going to label the circuit current sources just IB and IB rather than IB plus and IB minus. When we do IOS, we'll consider the case when those two currents are slightly off from one another. Okay, so again, we're going to use superposition. Okay, and I'm going to write this by inspection. I can write VO is equal to, first I have three sources here. So we're going to consider VI, turn off the two IBs, and we simply have minus RF over R1 times VI. All right, now we're going to add, let's consider, maybe I should call these I minus, IB minus, and IB plus just so I can distinguish them. Sorry. Let's look at IB plus. They'll ultimately have the same values, but okay, we'll use IB plus. We'll turn all the sources off except for the current that is the current source that's connected to the non-inverting input. Well, where does this current flow? It doesn't go through or go into the op-amp input because this is now an ideal op-amp. I'm going to cross this out and say this was moved to external. Right? I drew those on the circuit outside the op-amp, so now my op-amp is truly ideal. So there is no current going into my non-inverting input. So IB plus, the only place that current can flow is actually from the ground. So there is zero contribution to the output because that current flowing IB plus at my non-inverting input does not produce any voltage change at V plus. Right? And it certainly doesn't do anything over at V minus because the current doesn't ever get over there. Okay, and then lastly, we're going to consider IB minus. Okay, now this one's a little tricky. Maybe I'll redraw the circuit for a moment. I have IB minus. Okay, this goes into my inverting input. I have RF. VO. And over to the left I have R1, but it's ground, and I'm grounding VI, right? R1. So this op-amp is ideal. Now you might think initially, this would be the natural thing to think, say, okay, I have IB minus flowing from this node right here, and there are two other resistors connected to that node. I wonder if they're like in parallel, and so I do like a current division deal. Or I'll maybe do the parallel of them, and then take that parallel resistance and multiply it by the current and get the voltage that's at that node. But I say, wait a minute, this is actually no ordinary just passive network. This is an op-amp. And there's negative feedback, and the node we're talking about is the inverting input. So what do we know about an ideal op-amp that has negative feedback? Well, we know that the voltage between the non-inverting and inverting inputs is zero. So don't forget that the voltage between V plus and V minus is zero. And that means that therefore V minus is equal to zero. And that means that if the voltage at V minus is equal to 0, the voltage across VR1 is equal to 0, which then means that IR1 is equal to 0. In other words, R1 has no bearing on IB's effect at V out. Furthermore, because R1 is 0, it means that all of IB must be flowing through RF. So if I were to call, I'm going to label this here IRF. Now, other times I would label IRF pointing the other way, but here I'm defining it to the left, just it's convenient because now I can say IRF, therefore IRF is equal to IB. Right? All this current has to go this way. And this leads me then to say, oh, well, VO is going to be equal to V minus plus RF times IRF. Well, V minus is equal to V plus, which is equal to 0. And IRF is equal to IB, so therefore VO is equal to RF times IB. And now I can fill out my expression for VO. I have that VO is equal to the original inverting op-amp gain minus RF over R1 times VI plus an error term at the output, an offset term that is due to IB. Okay, and let's consider, okay, is RF IB significant? Well, it depends. Depends. On what? On, of course, how big IB is and how big RF is. So as an example, if IB is equal to 40 nanoamps, and let's say that RF is equal to 1 megaohm, okay, that's 10 to the 6, then IBRF is going to be equal to, what do we have, 40 times 10 to the 9 times 10 to the 6. So that's 40 times 10 to the minus 3, or 40 millivolts. Is that significant? Likely it is. It depends, I guess, on what your circuit is trying to do. Let's say that if R1, say, was 10K, okay, then we would have that VO is equal to minus 1 meg over 10K. That's 100, right? 100 VI plus 40 millivolts. Okay, well, if VI is, you know, what does VI range over? Let's say that VI is a really small signal that you're trying to amplify. So let's say VI ranges from plus and minus 0 millivolts to plus and minus, let's say, 10 millivolts. Okay, then that means this term here is going to range between minus plus 0 to 1 volt. 0 to 1 volt. Right? When you're actually, when VI is at its maximum value such that you're putting out 1 volt, well, now 40 millivolts out of 1,000 millivolts is, what is that? That's 4 out of 100. That's 4%. Right? But this is at VI is equal to 10 millivolts. But at VI equal to 1 millivolt, we would actually have minus 100 times a millivolt, so that would be 100 millivolts, or minus 100. And now we're talking 40 out of that. We're now talking 40%, right? So even a 40 nanoamp bias current could have a significant effect. Now, if instead of talking about a full-scale output voltage of 1 volt, let's say it was actually 10 volts, all right? Well, now all of these percentages would drop by a factor of 10. So maybe it's okay. It depends on what your circuit is trying to do. Now, how do you combat? Okay, how to reduce effects of IB? Okay, 1, reduce RF. Okay, so if you're trying to achieve a gain of 100, then instead of having 1 meg and 10K, maybe use 10K and 100 ohms, right? Or 100K and 1K. Now, of course, maybe you can't do that. Maybe there's a reason you need R1 to be large. R1 would actually affect the input resistance that you would see when you looked into the input Rn here is equal to R1. So if you need a certain input resistance, then you can't just arbitrarily make R1 small. Right? So that's the way you can counter it. But there's a clever way that you can counter it without having to reduce that RF, and I will show you that at this point. Okay, so we'll actually cancel IB effects, I think it's AF effects, by adding R3. Okay, so here's what we're going to do. Let's take our original circuit example. We had RF and R1 and VI. And what we're going to do is we're going to add a resistance here, R3. So let's go ahead and ground this. We're going to consider just the case of the effect on the output due to IB. Okay, only IBs, IB plus and IB minus acting. Okay, we're turning off VI because we don't need that to answer this. I'm going to draw the IB sources, IB minus, and here we'll see if I can fit it in here. IB plus. Okay, so we already know the effects of IB plus. We're going to do superposition again. All right, we already saw that we have RF times IB plus. That's from last time. What we haven't considered is the effect of IB minus. So when we turn off IB plus and we turn on just IB minus, then we have a non-inverting amplifier. Let's redraw this. If you think of this current source in parallel with this R3, all of IB minus goes through R3 because none goes into the non-inverting input. So this could be replaced. I could do a source transformation. Well, two things I could do. I could, one, just answer, say the voltage right here is going to be minus R3 IB minus, right? That's simply solved by considering that IB minus flows through R3 and generates a voltage across it, and the polarity turns out to be negative. Sorry, I got someone came in my office again. Okay, so we could do a source transformation and call this R3, and then this is minus R3 IB minus, right? And then this could be connected to my non-inverting input. But because the current is 0, right? This is an ideal op amp here. I don't really need, this is not needed in this case. So it's not necessary to do a full source transformation. All I need to do is calculate this voltage minus R3 IB minus. Okay, so now we have this minus R3 IB minus voltage applied to the non-inverting input, and our op-amp circuit is a non-inverting configuration, so we know that the gain for that is 1 plus RF over R1 times whatever our voltage is at V plus, right? And that voltage is minus R3 IB minus. Now, where are we going with this? I want to get rid of the effects of IB minus, or IB. So, we're going to force V to be equal to 0, optimistically hoping that we could choose R3 in such a way that these two terms are going to cancel each other. Force VO to be equal to 0, and assume IB plus is equal to IB minus is equal to IB. Okay, again, we'll consider next when that is not the case. But then we have 0 equals VO, or VO equals 0, is equal to RF plus, all right, R1 plus RF over R1 times, oops, there's a minus sign here, times R3. And I didn't even write the IBs because they cancel out. Well, I'll go ahead and write it here, I guess. Okay, so we're going to solve for R3. So we end up actually with R3. If you solve this, we'll find that R3 is equal to R1 RF over R1 plus RF. Wow, which means set R3 equal to the parallel combination of R1 and RF. Wow, this cancels IB effects. All right, super. So we could still use the 1 meg resistor. So let's do that. Say we had 1 meg ohm, and we had 10K here, and we have VI. And now all we're going to do is right here, we're going to set this resistance to be 10K in parallel with 1 meg ohm. And now my output is going to be back to being equal to only minus R. This right here is ideal plus IB. Ideal plus IB. Nevertheless, my output will be back to the ideal minus RF over R1 times VI plus no IB effects. Right? That's super. Okay? So, in practice, the thing you want to consider is, do you really want to find a resistance whose value is 10K in parallel with 1K, which is going to be something like 9.9, or is it good enough to just put in 10K? Right? And this is going to depend on your RF and your R1 values. But sometimes, because a real op-amp is going to have not only the bias effects, bias current, the offset voltage effects, and then the offset current effects, trying to zero one out completely may not be merited, because long before you totally zero it out, one of the other non-perfections in your op-amp will start dominating, and so there's a point of diminishing return. So maybe just putting 10K here would be good enough. I don't know. We'd have to actually work through an example. Okay, lastly, consider input offset currents, IOS. And this one is very close to the bias current. Okay, so essentially, if we have our two bias currents, I'll call it IB plus and IB minus. This is an ideal op-amp in here, right? We would define IB plus define. IB plus minus IB minus is equal to IOS. Okay, in other words, not necessarily zero, right? In other words, we're no longer going to assume the luxury of having bias currents that are exactly matched. In fact, they won't be, right? And if I go back to the transistor drawing, the differential pair, on the previous page, what this comes down to is the fact that there are slight variations in the fabrication of those two transistors. It's either from the semiconductor doping, where even though the concentrations of the impurities or whatnot may be quite close, because of the small geometry, there may be some localized differences in doping, or it might just be the precision or the accuracy, the uncertainty in the geometries of that device. Lithography, photolithography is used to produce the little transistors, and on the silicon die, and there are some precision, there's some accuracies in the feature size, right? So any variations could result in the bias currents not being exactly the same. Again, we don't need to worry about that other than that we want to capture that at a high level in our model. So we're capturing it by defining the difference between these two as IOS. And then we'll say that IB plus IB minus over 2 will be equal to IB. Okay. So we can then combine these two to actually express or solve for IB plus and IB minus in terms of IB and IOS. So let me think about how I'm going to do that. Let's cross this out and put 2IB here. I don't know, I'm doing this on the fly here. Let's see, and if I add these two, what will I get? I'll get 2IB plus, and then I'll get 0 IB minus, and I'll get 2IB plus IOS. So therefore, IB plus is equal to IB plus 1/2 IOS. And we could find similarly that IB minus is going to therefore be equal to IB minus 1/2 IOS. Okay, so the way you can draw this schematically, there's two ways you can do this. Well, one way being actually draw it schematically. The other way is to simply use what we've done so far with IB plus and IB minus, and then when you actually plug in values for IB plus and IB minus, you don't just put in IB and thereby have cancellation in the terms involving IB plus and IB minus, but you include the plus 1/2 IOS and minus 1/2 IOS. Here I'm going to show you graphically or schematically how to do it. Okay. So we'll have I'm going to draw this as IB, and I'll draw this one as IB. But then we'll add, in addition, we know that IB plus is IB plus 1/2 IOS. So I'm going to add another current source here, and this will be 1/2 IOS. And I'll add another current source here. And I could either point it up and call it 1/2 IOS, or I could point it down and call it minus 1/2 IOS. So I'm going to just be different, and I'll point it up and call it 1/2 IOS. Okay, and this now is an ideal op-amp with the effects of both bias current and input offset current both captured with the external sources that we've written. Now you could also just redraw this as a single source like this and call it IB minus 1/2 IOS, and do the same for the two current sources connected to the non-inverting input. Let's work an example again, and we'll end with this. So if we take again the inverting amplifier with RF and R1, and let's say that we actually have already added in our R3, which is equal to R1 in parallel with RF. Okay, so this here has its ideal plus IB plus IOS. So we'll go ahead and include IB. But because I have already added my R3, that's R1 and RF in parallel, I already know that I have canceled the effects of IB. So I'm going to go ahead and fill out what I know I can write, which is minus RF over R1 times VI. I'll also say it's plus 0 IB. This is going to be due to, or thanks to R3 equal to R1 parallel with RF. And then now we don't know what this is. Right? That's what we need to find out. So to capture this, we will add, I'll add this current source. Let me go ahead and redraw it. So this is ideal. RF and R1, and I'm going to ground this because we're going to look just at the case of the IOS. Okay, I'll connect this to ground R3 here, and now I have to add in my two current sources. Now I could do the full IB plus 1/2 IOS and IB minus 1/2 IOS. Could do that, but there's no point in it because the IBs I know will actually cancel out thanks to the addition of R3. So I'm only going to add in the IOSs. Okay, so this is akin to doing superposition where we said, well, we're going to consider the IB plus and IB minus, or the two IB independent sources separately, and right now they're turned off. So VO due only to IOS is going to be as follows. We still have to do superposition. Okay, so if I, the fortunate thing is we already know the results for both of these because these current sources have already been considered when we did the IB. So let's consider the case where the IOS, we'll do this one here first. We'll do this one second. So the first term, we already saw that when we do superposition, all the other sources are off. We found that the V plus is at 0, and therefore V minus is at 0, and therefore there's no voltage across R1, therefore there's no current flowing through R1. Therefore, all of this 1/2 IOS flows through RF. So we'll have RF times 1/2 IOS. That is due to this first source here. Then we will consider the second source, which is tied to the non-inverting input. Notice that the current source is pointing down, but its value is minus. So let's visually, in our mind's eye, envision this going up, and I have 1/2 IOS going up and into R3. So the voltage I have here is, I have 1/2 R3 IOS going into a non-inverting amplifier. Right? So we'll have RF over R1. So go ahead and write that. 1 plus RF over R1 times 1/2 R3 times IOS. Now I'm not satisfied with this form. Let's clean it up. So it's the second term I want to work on. This R3 is equal to R1 RF over R1 plus RF. This term here is R1 plus RF over R1, right? And then these cancel, and this cancels, and so what I end up with is 1/2 RF times IOS, which is the same term as I had for number 1. So therefore we can write that VO due to IOS is equal to RF times IOS, because I have two 1/2 terms. So now I can write that up here. RF times IOS. And we're back to considering the magnitude of RF. So to minimize the effects of IOS, limit RF magnitude. Or, where not possible, buy a better op amp. And that's why we have so many flavors of op amps. Okay, well, got it in just under an hour. Thought I could do it much shorter, but at any rate, hopefully this is helpful and practical, since I worked some examples of how you both, what are the 3 DC imperfections, common DC imperfections of the op amp, and then how you model them and how you incorporate them into your circuit analysis. I guess the fourth, the last per se DC imperfection, which I think you would already know about, is finite open loop gain, right? But when we first introduced op amps, we actually started off not assuming that AOL was infinite, and we then took the limit. So I don't think we need to go back over that. That's something you have seen in the course of just being introduced to op amps. So we'll finish it here. Hope this was helpful, and see you next time.